So you see three equations up on the board here, all three clearly for electric fields. How do we know, by the way, besides the variables, besides the fact that we're familiar with these equations, what one thing can remind us that these are for electric field versus kinetic or potential or whatever other kind of energy that we have, Travis? Yeah, we see that vector sign, right? I've told you guys 100 times, don't forget to put that vector sign over it, because at some point, not today, not tomorrow, but 2 months down the road, you will mix up energy and electric field if you don't consistently put the vector sign over it. So we see these three equations, all for electric fields. One is for a producer, one is for an experiencer, one is for parallel plates that we introduced the concept of yesterday. We circle the first two equations. These two equations are all valid when, or both valid, I should say, when. For electric fields, yeah, but specifically for non-uniform electric fields. Now, we have a non-uniform electric field when we're dealing with something like this. Right, we got, say, a positive producer that produces a non-uniform electric field, an electric field that changes depending upon where you are. How do we say that that second equation is valid in that situation? Okay, that's a producer, right? Shouldn't we always use the producer equation, the first equation, when we have that situation? Well, if all you have is data about that producer, then yes. Okay, but the second equation is certainly valid when we have this non-uniform electric field, okay, this electric field that you see on the right-hand side. Okay, the difference is that if you have a little test charge in there, whether it's a positive or a negative, it doesn't really matter, a little experiencer, then we can use that second equation. We still have that non-uniform field. We still have the field that was caused by this point charge, this point source. Okay, but that electric field is experienced by some other charge. Okay, we're allowed to use both of these equations whenever we have that non-uniform field. Okay, the first one, if we have information about the producer. The second one, if we have information about the experiencer. We're also going to circle the last two equations. They're both valid when we have a uniform electric field. And when do we have a uniform electric field? Yeah, when you have two parallel charged plates or things that approximate two charged parallel plates. I'll give an example of something that approximates charged plates in just a moment here. This time we're going to swap the plates. Yesterday the top plate was positive, the bottom plate was negative. Reverse this time. Which way does the field point? Good. The field's going to point upward. It's a uniform electric field. The field lines are parallel to each other. Now, this equation down here, E is equal to delta V over delta D, obviously we can use that for these parallel plates. But again, what about that middle one? Well, as long as we have something in between here experiencing the field, whether it be a positive or a negative, doesn't matter where it is. As long as we have something experiencing that field, then we're allowed to use that middle equation as well. So in a sense, you get two producer equations, the first one and the last one. The first one is for a non-uniform electric field, like we've dealt with up until yesterday. The third one is for the uniform electric field, like we dealt with yesterday. The middle one, okay, whenever we have an experiencer, no matter what kind of field it is, okay, uniform or a non-uniform field. Make sense? One more little thing before we go over and check the homework here. There's two variables here that we're not all that familiar with here, delta V and delta D. Remember what that stands for? You don't really understand that one yet. You won't until Monday. What is it? Yeah, it's volts. We call it the potential difference. And it's going to be measured in volts. It's related to the energy of the charge between the two plates. Okay? And delta D is what? The distance what? Good. It's the distance between the plates. Now, we know that. I addressed that yesterday. But in the end, guys, at some point, it's quite possible, I wouldn't say probable, but quite possible that you'll see a question like this where you're told this charge right here, let's say, is 2 centimeters from this plate, and it's 8 centimeters from the top plate. Okay, what's the electric field between those two plates? And some of you, when you go to say delta V over delta D, will use delta D as 2 centimeters. Some of you will use it as 8 centimeters. Those of you who do it correctly will do it as 10 centimeters, right? It's not the distance from one of the plates to the charge, it's the distance between plate and plate. Doesn't matter where the charge is in between those plates, it's a uniform field. Okay, what matters is the distance between the plates. All right, 2 questions for homework last night, page 568. Any issues with those 2 questions? No? Easy questions? Yes? All right. Remember the homework that I assigned yesterday as well for Monday? Worksheet number 8, right? So let's make sure that we have that done. Anybody start worksheet number 8 last night? Yes? How's it going for you so far? Okay. Okay. I'm not going to do that right now because I want Max, everybody else to have a chance to take a look at that first. But if you want to stick around after class for a second, if you're struggling with that, then I can give you a hand with it, okay? All right, we got a couple multiple choice questions for you here. I'd like you to take out your phones and submit these ones together. So we're going to submit it as multiple choice number 1. And we're going to submit it as numerical response number 1. That's on page 35 of your worksheet booklet, okay? 47 and 48, you're submitting as multiple choice number 1 and numerical response number 1, please. Sorry, one little thing that I wanted to mention to you guys before you take a look at these questions, okay? These questions came from, I believe, 2002, so they're pretty old questions. It was when we had a different Physics 30 curriculum. It was largely the same as it is now, but slightly different. One of the things that we were required to do prior to the curriculum change 5-6 years ago was something called transformers. We don't need to know anything about transformers now. Now, could we see something about transformers on the exam? Sure. Sure we could. As a context, right? But not as a, you know, you need to know details about it. You need to have learned details about it. Okay, this question actually requires you to know a little bit about transformers, just because it's an old question. Okay, right, I'm just going to tell you basically what you need to know. Okay, what you would have known had this been 8 years ago, and you would have learned about transformers already. We talk about a primary coil and a secondary coil. This is the primary coil. This is the secondary coil. Don't worry about how it works right now. It says the 12-volt direct current is in the primary coil. The 20,000-volt potential difference is produced in the secondary coil. And it's the secondary coil that we're concerned about here, right? Because we're talking about right in here, the spark plug. So when you're using a potential difference, it's not going to be this 12 volt here, it's going to be the 20,000 volt. Again, if this was 10 years ago, you'd know that because we would have learned about transformers. If you ever see a question like this on an exam, they'll explain that. You could see a transformer, but they would explain exactly what I just explained, okay? You wouldn't need to know that ahead of time. Okay, so page 35, let's take a look at those 2 questions, 47 and 48, please. All right, of the responses that we've gotten here, literally 100% of you got the correct answer for 47. That's good. Okay, it is a rather straightforward question, okay, but usually even when we have a straightforward question, somebody gets it wrong. Okay, we want to find the electric field strength between induced in the gap of the spark plugs here, the electric field strength. Now, we've got 3 equations for electric field. There's the producer equation, there's the experiencer equation, then there's the parallel plate equation. Listen, we have here a gap of 2 millimeters. That's going to be the distance between the electrodes of the spark plug. We have a potential difference of 20,000 volts, delta V. We got delta V and we got delta D. Then let's use those 2 numbers in order to calculate electric field. 20,000, this is what I was really happy about. Everybody, every single person recognized that you've got to convert that millimeters to meters. Okay, 2.0 times 10 to the minus 3 or 0.002 meters. When we do the math on that one, okay, it ends up being D 1.0 times 10 to the 7 newtons per coulomb. So this gap in the spark plug, these electrodes of the spark plug, approximate 2 parallel plates. So, okay, ask you the question here. Where do we see these parallel plates in real life? Well, in the gap of a spark plug. Okay, where else might we see them? Well, maybe it's in bumper cars, right? The top metal plate and the bottom metal plate of the bumper cars. There's an electric field between those. Okay, where else do we see them? There's lots of places. You see a few more examples before we're done of where you can see those. 48 didn't go quite so well for us. Not badly, but not quite so good. I've got answers of 4928, 2014, 1818, 113, 2512, 5009. I've got I don't know, and I've got nope, and I've got something else that I don't understand, some sort of code probably. Listen, we want to find an acceleration. We know what we do. We always use F is equal to m times a. But to do that, we need a force, right? Well, how do we find a force? We know that these electrons are experiencing a certain electric field. What electric field do these electrons experience? How about 1.0 times 10 to the 7? So let's say electric field experienced by the electrons is equal to F over Q. Okay, we don't want to solve for F here because we have E. The electric field experienced is the same as the electric field produced by the plates. It's 1.6 times 10 to the minus 19 coulombs times the electric field of 1 times 10 to the 7. Gives me 1.6 times 10 to the minus 12 newtons, which we're promptly going to plug into here. Divided by the mass of the electron. And what do we get when we do that? 1.8 times 10 to the 18. Now, how do we express this? Okay, we want it as A, B, C, and D. We want the values of A, B, C, and D. Okay, so we're going to express that as 1818. If they said B times 10 to the W, what's the value of B? Then we would have said 1.8. Make sense? Good? All right. Let's move forward and see if we can finish this nice little topic up today. It's a relatively small one. Today we're going to talk about conductors, electric fields, and charges that exist, excess charges that exist in or on these conductors. First, I want to define a term. Define this in Physics 20, but we'll define it again now. Static equilibrium. Static means not moving, at rest. Equilibrium means balanced forces. So static equilibrium would mean charges at rest not moving around. Charges at rest not moving around because the forces acting on them are all balanced. Okay, they're not going to go anywhere because everything is balanced out. In other words, no net force. If we have excess charges on a conductor or in a conductor, right, extra electrons, let's say you have 1,000,000 protons, maybe you've got 1,000,005 electrons, or maybe you've got 1,500,000 electrons. You've got extra electrons, or for that matter, less electrons. But you've got a net charge. You've got extra charges. Where do those extra charges go on or in a conductor? Where do they go? Well, today we're going to talk about a few different shapes of conductors, a few different scenarios, and see where those charges go and what the charge distribution looks like. The first thing that we have to recognize with all of these shapes, whatever they are, is that these extra electrons will move around until they reach this point of static equilibrium. Okay, if the forces are unbalanced, then that's going to cause the charges to move. Right? If I push on Dallin with a force of 20 newtons one way, and Brett pushes on him with a force of 50 newtons the other way, he's going to move. The only way he's going to remain at rest is if the net force acting on him is zero. In other words, if he's in static equilibrium. He will keep moving around until the net force acting on him is zero. The excess charges in a conductor will do the same thing. Eventually, however, the forces will balance and they will be in this point of static equilibrium. The first shape that I want to look at is a solid conducting sphere. It's like a marble, except it's made out of a conductor instead of glass. Everybody take a look at the diagram down here, okay? diagram A down here. We've got three charges. We're going to call this one charge number 1, charge number 2, and charge number 3. I want to focus on charge number 1 for a second here, although the same analysis applies to the other two charges as well. In fact, we could have 1 million charges on here, 1 million extra electrons in there. The same analysis would apply to all 1 million of them. It's just a little bit more complicated to see, that's all. As a result of charges 2 and charges 3, charge 1 will experience two repulsive forces. It experiences a force up this way that we're going to call F21, the force of 2 on 1. 2 repels 1 away from number 2, right? The force of 3 on 1 is up this way. So you got a force up, kind of up and to the right. You got a force up and to the left. What happens to charge number 1 as a result of both of those forces? It's going to want to go straight up. It's going to want to go up here. But when it hits the surface, what happens to it? Unless this air out here is a really, really good conductor, where normally it's not, right? Normally air is a pretty good insulator. Okay, unless it's a good conductor, then that electron, when it hits the surface, is going to stop, because it doesn't want to go from a conductor to an insulator, right? It wants to go as far up there as it can within the conductor. But when it hits the surface, it stops. So now what you're going to have is this electron that's reached that point on the surface right there. What do you think is going to happen to charge 2 and 3? Same things. So in effect, in the end, what you're going to have is these 3 excess charges all going to the surface. And what do you notice about the distribution of them? They're evenly spaced. Now, this is a 2-dimensional diagram. This would happen on a 3-dimensional scale, right? If this was a solid conducting sphere. In the end, on that 3-dimensional sphere, they would go to the surface and they would be evenly spaced on the surface. That makes some sense? Okay. These blue lines here, real quickly, these blue lines, what do you think they represent? The electric field, right? The electric field points toward a negative producer. Why? Well, because ultimately it points toward the individual excess electrons on that negative producer. Next, we've got not a solid conducting sphere, but rather just a plate, right? Just like a flat plate. You can see in the first diagram here, let me cover up the last couple pictures here. In the first diagram, we've got 3 excess charges essentially randomly distributed here. Now, I want you to take a look at the middle charge. The middle charge, and I want you to take a look at the 2 forces that exist on the middle charge as a result of the other 2. We're going to call this one number 1, number 2, and number 3. Number 2 experiences 2 forces, a force of 1 on 2 and a force of 3 on 2. The force of 1 on 2, because they're both negative charges, is going to be to the right. It's repelled by number 1. Make sense? The force of 3 on 2 is to the left. Number 2 is repelled by number 3. F32 to the left. Why do I have F12 drawn quite a bit bigger than F32? Why is that a bigger force, Patrick? But why will it go more to the right than to the left, Travis? Sorry? Yeah, F is equal to KQ1, Q2 over R squared. And if this distance is smaller than this distance, then this force, F12, is going to be bigger than F32. Make sense? So what's going to happen, Patrick, to charge number 2 as a result of both of those forces acting on it? It's going to move more to the right. It's going to move in the direction of the net force, which is to the right. So as it moves to the right, what's going to happen to the value of F12 as it moves to the right? It's going to decrease. What's going to happen to the value of F32 as it moves to the right? It's going to increase. There's going to come a point when F32 and F12 are the same values, right? What's happening at that point? We're in static equilibrium. The charges are now not going to move. So when is that going to happen? It's going to happen when the second charge is midway between the other 2 charges. So in other words, when these charges are evenly distributed on the outer surface of this plate. Same as it was for the solid conducting sphere. Does that make sense? excess charges, whether you have a uniform solid conducting sphere or whether you have a uniform solid conducting plate. If it's a uniform object, then the charges will go to the surface. Not all the charges, but the extra charges will go to the surface, and they're going to be evenly distributed. Right, Josh? And of course, in the bottom diagram, it's just showing the electric field lines again. Well, this one's a little bit ugly. Here we have an irregularly shaped object. They don't have it drawn quite as a point, as a pointy object, but you can see it's more pointy than the other ones were. It's not uniform, right? Up until here, it's been uniform shapes. Now it's a kind of a pointy shape. I want to cover up a little bit here, and I want to draw a picture on diagram A. We're going to forget about this one right now because we can simplify this diagram a little bit. We'll call this one number 1. We'll call this one number 2. We'll call this one number 3. Okay, charge number 2 experiences a force due to number 1. It's going to be this way. We'll call that the force of F12. Agree? There's also a force of 3 on 2, and it's going to be this way. Agree? Well, what's that going to do? What are those two forces going to do? The first thing they're going to do is apply a net force, or supply, I should say, a net force that pushes it to the outer surface if it's not already on the outer surface. In other words, the net force is going to be this way somewhere, so it pushes it again, if it's on the inside here, out to the outer surface. It doesn't go beyond that because the air is presumably an insulator. So it goes to the outer surface, but the question now is, where on the outer surface does it go? Are they evenly distributed like they were in the last two diagrams, or are they going to be not evenly distributed? Are they going to be closer together somewhere than somewhere else? Now I want you to take a look at F12 in the x component. We'll call this our x-axis. F12 in the x component of F32. F12 wants to push this electron out to the tip of this pointy surface, right? Wants to push it out to the point. The x component of F32 wants to do what? It wants to pull it back from the tip, right? Which one wins? F12 wins. Why? Yep. Well, no, you can assume the distance is more or less the same there. Right? Good, good. F12, its entire force is pushing it out to the tip. F32, only part of the force is pulling it back. Part of it is pushing it out to the surface, right? So along that axis, all of this force is pushing it out. Only part of this force is pulling it back. So F12 is going to win. What's going to happen to charge number 2 as a result of that? Goes to the surface, but where on the surface does it go? Closer to the tip. Now, as it gets further away from charge 1 and ultimately closer to charge 3, what's going to happen? At some point, they're going to balance each other, right? This force will become bigger, this force will become smaller, and they're going to balance each other. But they're not going to balance each other when they're equally spaced like they did in the last two pictures. They're going to balance each other now when these charges here, charge 2 and charge 3, are closer to the tip. So what do you know about non-uniform objects? The charges get more concentrated where it's pointy. Does that make sense? You get more concentration of charge, and therefore a stronger electric field at pointy things than you do at flat things or rounded things. Does that make sense? That's why when you walk across the carpet with your leather-soled shoes and you go to touch somebody and give them a shock, that's why you don't kind of swing out your hip and touch them with your hip and try to shock them that way. Okay, what do? You touch them with your fingertip. Why? Because your fingertip is more pointy than your hip is. So it's got a bigger charge buildup on your fingertip than it does on your hip. There's a bigger electric field on your fingertip than there is on your hip. There's a bigger chance of discharging from your fingertip than there is your hip. Now, your fingertip's not a conductor, so it doesn't work quite as well as if it was a metal pointy thing, okay, but it still is the same idea. Does that make sense?